We're now ready for the last section in chapter 7 that we're going to do, and it's how we talk about hypothesis tests when we need to use the student's t-statistic. So let's come over and look at what we did last time, and let's just do a quick overview. So last time, what we did was when we needed to test a statistic, we created the hypotheses, we created our test statistic, and we used this formula. We found our p-value, and then we came to our conclusion. Well, it turns out that this time is going to be really pretty similar. Our hypotheses are going to be the same. So we'll use the exact same hypotheses whether we're doing one test or not. The test statistic is where it changes slightly. Instead of using the z equation, we're going to use the t equation. And instead of using our standard deviation sigma, we're going to have to use our standard deviation s. So what's the difference? The difference is that sigma comes from the whole population, s comes from just your sample. It's always worth asking, when do we use this? We use this when our sample is small and sigma is unknown. So if we're in a situation where the problem doesn't tell us what sigma is and we have a fairly small sample, what's small? The standard is less than 30, but it's kind of a judgment call as to what's small enough. But if we have a small sample and sigma is unknown, then we switch. We switch our z to a t and our sigma to an s. Okay. Now, when we find a p-value, our p-value is the exact same picture. The only difference is we're using our t, so we're using whatever answer from t was above, and instead of using the normal command, we're using a t command. And for t command, we need degrees of freedom, and so we use n-1 for degrees of freedom. So if you're using the app, we're going to come to our t command instead of normal. And if you're using your calculator, you're going to go to tcdf. And if you're using your Excel, you're going to do t-distribution. So you're going to use the t command instead of the z command. Finally, we draw a conclusion, and the way we draw a conclusion is the exact same. So once we have that p-value, we do the same conclusion drawing that we did before. So the good news is this problem is really similar. We just made one small adjustment, and that is we change our formula here, and we change which buttons we push on our technology. Okay. So let's tackle this problem where we have flies and we're trying to figure out how big the flies are. The first thing you're going to need to do, if we have a set of data, so you suspect the flies in your house are larger than normal, you look up online that lengths of flies are normally distributed with mu equal to 6.3 millimeters. So you catch 7 flies, measure their length, and your results are 5.7, 6.2, 7.4, 7.1, 6.7, 6.5, and 6.2 millimeters. So what we need to do is we need to first we kind of need to go calculate some things. Oh, well, actually first let's write down hypotheses and kind of get this problem started. Okay, so the first thing you'll notice is that our hypotheses, we're trying to compare our flies to what we know is the size of flies nationally. So how big are flies normally? If there are no difference between our flies and all other flies in the world, then our flies are going to have a mean of 6.3 millimeters. But we've been watching our flies and they feel like they're really big. So we are going to use our alternative hypothesis that we believe that our flies are actually bigger than the national average. So notice this, if there's no difference between our flies, this is our number. If there is a difference and what we're trying to prove is true, then our flies are bigger than that number. All right, so we're already now able to observe a few things. First, you'll notice that this is a right-tailed test. It's right-tailed because we're using the greater than sign right here. And the next thing we know is that we're going to need to use a t-distribution for this test. Why? Well, notice we only have 6 flies, or 7 flies, so that's definitely a small sample. And then the second thing is that you'll see nowhere in the problem does it tell us what the standard deviation is. So we have no standard deviation to work on. We don't know we don't know how many flies. So we have 7 flies and no sigma in the problem. So we don't know what sigma is. We have a very small number of flies. T-distribution is the way to go. Okay, so what we need to do now is we need to go calculate sigma and x bar for this problem. So you need to grab either your calculator or Excel or some other way of computing this and take these values, take our 5.7, our 6.2, 7.4, 7.1, 6.7, 6.5, and 6.2. And you need to go calculate those on your own. So grab your device and put these numbers in and find the mean and standard deviation. If you don't know how to do this, this would be a really good time for you to drop by study hall hours and we can work on this together. Okay, I'm going to type them in. Sorry for the delay. You can be working on your own at the same time. Okay. Okay, so hopefully you got that done. If not, you might want to pause it now and go ahead and finish doing that. But what I got was 6.54 for my average and then 0.558 for my standard deviation. I use the S. I use the sample standard deviation. So these are the numbers that we're going to need to use. Why do I need these numbers? Well, these are the numbers that go into my formula. And so if the problem doesn't tell us these numbers, we have to calculate them ourselves. Okay. So now that we have our hypotheses, we figured out what type of test we're doing, we figured out the numbers that go into our formula, we're ready to start calculating our test statistic. Our test statistic is T. And so T from earlier was x bar minus mu divided by S over the square root of n. So all we have to do now is pick the right numbers out of our problem and put them in. So 6.54 is our x bar. That came from the average of these numbers. Mu is 6.3. That comes from the null hypothesis. S is that 0.58 that came from our numbers we just calculated, and N is how many flies we've got. We have 1, 2, 3, 4, 5, 6, 7 flies, and so N is 7. So here's our test statistic, and so we need to now type this into our calculator, and the same warnings as we had last time apply. You should be careful not to how you type this in. So these need to be grouped together, and these need to be grouped together. All right, I got 1.09. Let's go ahead and add a 5. Whether you do 9 or 9.5, it's not really a big deal. Okay, I got 1.09 for my t-distribution. So this is my t. So now I'm ready to come and calculate my p-value. So this is my test statistic. This is worth circling probably. And now I'm ready to do my p-value. I know from the fact I used a greater than earlier, I know that I'm going to put 1.095 on here, and I'm going to shade the greater than side. So I know that p is going to be this right-hand side. Now what do I need to use? I need to use my t button, and I need to use my degrees of freedom are going to need to be 6 because it's 1 less than however big my sample is. So let me grab my app. Again, feel free to use your calculator or computer. They're both capable. But I'm going to use my app and come down here, and we're looking for t. So yeah, you'll have to scroll down a little bit. And there's t, and we'll click on it. This funny letter here is a nu, and this is the number we're going to use. We're going to use 6 for that. And then I'll do 1.095 and hit enter. And notice I've got the left-hand side. That's not the picture that I want, is it? I want the right-hand side. So I'm going to switch to that picture. So now I've got the picture that I want. So what is my p-value? My p-value is 0.158. So 0.158 was my p-value. Okay, so now we're at a point where we're ready to draw our conclusion. So we're going to compare this to our alpha of 0.05. So if alpha equals 0.05, what's the relationship between P and alpha? Which one's bigger? P is bigger. So we're in the case that P is greater than alpha. And if P is greater than alpha, so notice alpha is where we decide if we have a small probability. Did we have a small probability? No, we didn't have a small probability. So are we able to reject? No, we're not able to reject. So small probabilities you can reject and we're happy. Big probabilities you are unable to reject. And so we are not happy. Oh, I guess your happiness shouldn't be dependent upon what we get on a stats problem. But at any rate, we fail to reject H naught. What does that mean for our flies? We do not have evidence that our flies are larger. So we don't have evidence our flies are larger. For all we can tell, our flies might be the same size as every other fly. Now, I will say a few things. One, we only had 6 flies, so maybe if we'd gathered 60, we might get a different result. So as we know, the bigger your sample size is, the more power your test is going to have to reject things. But right now, at this point, we can't come to any conclusions. Okay, what you should do is you should try the problems on 7.5. So homework section 7.5 on page 43. You should go try those problems, and you should watch the next 2 videos. So what I'm going to do are the problems 7.7 and 7.8. I'm going to put them on their own videos on the next video, and so I want you to take a break, try both of those problems, see if you can be successful, and then come back and watch the video. So try them first. I'll put them in a separate place so you can come check them when you're done attempting them. All right, good luck, and I'll see you later.